By 2050, the world will own 5.6 billion air conditioners. That's up from 1.6 billion today, according to the International Energy Agency. And it works out to roughly 10 new units sold every second day and night for the next 24 years. That is not a typo. Picture a warehouse the size of a football stadium, packed floor to ceiling with air conditioners, and then picture a truck pulling out of it every 6 seconds to deliver them somewhere hot. That is the pace the entire planet is about to run at. Here's the part almost nobody's talking about. Every one of those units cools the room it sits in by dumping heat straight outside, into streets that are already baking, into a power grid that is already buckling under record demand. China found this out the hard way in August 2026, when a heat wave pushed its northern grid to an all-time record, driven almost entirely by millions of air conditioners switching on at once. So while most of the world keeps stacking up individual units and hoping the grid holds, one Chinese city quietly built something else. Not a better air conditioner. A way to make an entire district cold without switching on a single split unit in most of the buildings inside it. Stick around, because by the end of this, you'll understand why an underground ice factory in Shenzhen might matter more to your summer than anything sitting on your windowsill. And if you want the deep dives like this one every week, the subscribe button is right there. Air conditioning has one job, and for over a century it has done that job the exact same way. In 1902, an engineer named Willis Carrier built a machine to control humidity in a Brooklyn printing plant. And the side effect, cooler air, turned out to be worth more than the original problem he was solving. By the mid-20th century, that machine had shrunk down into a box that any household could bolt into a window, and the idea behind it never really changed. One unit, one room, one compressor working alone against the heat outside. America adopted it first and adopted it completely. By the 1970s, air conditioning had gone from a luxury to something close to an assumption, reshaping where Americans chose to live and how cities in the hot South were even allowed to grow. Architects stopped designing for airflow because they no longer needed to. The box in the wall did the work that building design used to handle for free. China came to the party decades later, but it came fast. As the country urbanized through the 1990s and 2000s, air conditioning stopped being a status symbol and became a basic expectation in a country where summer temperatures in cities like Shenzhen and Guangzhou regularly climb past 35 degrees Celsius. Domestic manufacturers rose to meet that demand, and companies like Gree, Midea, and Haier grew into some of the largest appliance makers on Earth, almost entirely on the back of it. The model that built America's summers became the model that would build China's. Here's what that dominance actually looks like today. China is not just the world's biggest market for air conditioning. It is the world's factory floor for it. Haier alone runs manufacturing operations that account for a huge share of global home appliance output. And Gree has grown into the largest dedicated air conditioner manufacturer on the planet by unit volume, exporting compressors and split units to every hot region on Earth. And the growth is nowhere close to finished. The IEA projects that China, India, and Indonesia together will account for half of the entire 5.6 billion unit global AC stock by 2050. 2 out of every 3 households worldwide could own an air conditioner by then. And a huge share of that expansion runs directly through Chinese factories and Chinese living rooms at the same time. For decades, this looked like an unqualified success story. Cooling that used to be a luxury for the wealthy became something a factory worker in Chongqing or a shop owner in Wuhan could afford to install in a single afternoon. Individual air conditioning solved the heat problem so completely and so cheaply that almost nobody thought to ask, what happens when hundreds of millions of these units all switch on within the same few hours of the same brutal afternoon. Turns out somebody should have asked. Because the system that made China the world's most air-conditioned country was quietly building a problem into its own foundation, one that would surface the moment enough of those units were running at once. Here's the honest reason individual air conditioning was never going to scale forever. It has a flaw baked directly into the physics of how it works. And it is not a minor one. An air conditioner does not destroy heat, it moves it. Every unit pulls warm air out of a room and pumps it straight back outside through a condenser coil, which means every single air conditioner in a city is, in a very literal sense, a small heater pointed at the street. Multiply that by tens of millions of units running in the same city on the same afternoon, and you get a measurable rise in outdoor temperature, the effect researchers call the urban heat island. The hotter the city gets outside, the harder every unit has to work to cool the inside, which pushes even more heat back out, which makes the street hotter still. That loop alone would be bad enough. But it collides with a second problem, this one electrical. Air conditioners do not draw power evenly across the day. They spike hard in the same 3 or 4 hours every hot afternoon. When the sun is highest and everyone is home or at work, with the thermostat cranked down. Grid operators have to build enough power plant capacity to survive that narrow spike, capacity that then sits mostly idle the other 20 hours of the day. In August 2026, that theory stopped being theory. A heat wave pushed electricity loads across northern, northeastern, and eastern China to record highs, with regions like Hebei, Tianjin, Liaoning, and Shandong all setting new peaks within a single week, driven almost entirely by air conditioning demand. The State Grid Corporation had to begin optimizing operations and preparing emergency cross-region power transmission just to keep the lights on. The machine built to solve the heat problem was now one of the biggest threats to the grid underneath it. If you wanted to fix this, you would need a city with almost no legacy to work around. Most Chinese cities were already built by the time this problem became obvious. Every building already locked into its own individual condenser units. Every rooftop already crowded with equipment nobody was going to rip out. Retrofitting an entire existing skyline was never going to happen fast enough. Shenzhen's Qianhai district didn't have that problem because in the years that mattered most, it barely had a skyline at all. Qianhai was established in 2009 as a special cooperation zone between Shenzhen and Hong Kong, built largely on reclaimed land along the Pearl River, with a mandate to become a financial and technology hub that could pull capital and talent across the border. That meant Qianhai got something almost no major Chinese city had: a genuine blank slate and a narrow window to decide, before a single tower broke ground, how the entire district would actually work. The constraint was brutal and specific. Shenzhen sits in a subtropical climate where summer temperatures and humidity punish buildings for most of the year, and Qianhai needed to attract the kind of high-value office tenants, banks, tech firms, financial services companies who expect world-class infrastructure from day one. Building tens of thousands of individual air conditioning units into a brand new financial district, only to hit the same grid and heat island problems Shenzhen's older neighborhoods were already living with, would have undercut the entire premise of the zone. So in 2014, Qianhai's planners made a decision that most cities never get the chance to make. They decided to treat cooling the same way they treated electricity and water, as core infrastructure to be engineered into the district from the start, not left up to whichever developer built which tower. Here's what that decision looked like in practice. A company called Shenzhen Qianhai Energy Technology Development was formed specifically to design, build, and operate a centralized district cooling system for the entire zone, rather than leaving each building owner to install and run their own equipment. The plan was enormous by any standard. 10 cooling stations, connected by roughly 90 kilometers of underground piping, delivering a combined 400,000 refrigeration tons of capacity across the district, enough to serve shopping centers, office towers, subway stations, and data centers alike. The total investment came to roughly 4 billion yuan, close to 620 million US dollars. Funded as public infrastructure rather than left to private building owners to sort out individually. But the real decision that mattered wasn't the scale. It was the technology underneath it. Qianhai's engineers didn't just install bigger, centralized versions of the same electric chillers everyone already used. They paired those chillers with something most cooling systems ignore entirely: ice storage. The logic was almost stubbornly simple. Electricity demand collapses at night when the city sleeps and the grid has enormous slack to spare. Cooling demand, meanwhile, peaks in the exact opposite hours, the hottest part of the afternoon, when the grid has the least room to give. If you could somehow move the electricity draw for cooling out of the afternoon and into the middle of the night, you could break the entire feedback loop that was already straining grids elsewhere in China. That was the bet, not a better air conditioner. A way to decouple when the cooling gets made from when the cooling gets used. For a long time, engineers considered this idea close to impossible at real city scale. You cannot simply run air conditioning at night and expect the cold to stick around until the following afternoon. Cold air is not a substance you can bottle. The moment a chiller stops running, the chilled air in a room mixes with everything around it and disappears within minutes. Here's where it gets interesting. The obstacle wasn't storing cold air. It was that engineers were thinking about the wrong physical form entirely. What if the problem isn't storing the cooling, it's storing the wrong thing? Air can't hold cold for long. Ice can hold it for hours. Picture Qianhai's cooling stations as batteries, except instead of charging electrons into a cell, they are charging cold into solid ice. Every night while the city sleeps and electricity is cheap and abundant, Qianhai's chillers run at full tilt, freezing enormous underground tanks of water into blocks of ice, essentially charging the battery to full. Then through the day, as offices fill up and temperatures climb, that stored ice slowly melts, chilling water that gets pumped through 90 kilometers of underground pipes into buildings across the district, discharging the battery exactly when the city needs it most, and exactly when the regular power grid can least afford to give anymore. The number that proves it actually worked came from Qianhai Energy itself. Once fully built out, the system is projected to save 130 million kilowatt hours of electricity every year, compared to the same district running on individual air conditioners, while cutting roughly 130,000 tons of carbon dioxide annually. That's not a marginal efficiency gain. That's an entire district's worth of afternoon grid stress, quietly moved to a time of day when nobody is fighting over the power. It sounds close to a clean solution to the whole problem. It isn't quite. Before you get too excited about ice batteries solving the world's cooling crisis, there's a catch, and it's a real one. The first honest hurdle is that Qianhai's biggest advantage was never really the ice storage, it was the blank slate. Building a 90-kilometer underground pipe network is dramatically easier when there are no existing buildings, no existing pipes, and no existing property owners to negotiate with. Retrofitting a district cooling system into an already built city means tearing up streets that already have gas lines, sewer lines, and subway tunnels running underneath them, while asking thousands of individual building owners, each already locked into their own AC systems, to buy into a shared network instead. That is an enormously harder sell than designing it in from day one. Second, the money. Qianhai's system cost roughly $620 million for a single district. Financing that kind of capital-intensive infrastructure requires long-term confidence from investors and building owners alike, and research groups, tracking district cooling as a climate solution. Note that projects like this routinely stall on financing, uncertainty, and regulatory friction, particularly outside wealthy financial hubs with government backing behind them. Third, and maybe most important, district cooling only really works efficiently in dense mixed-use commercial districts like Shanghai. The vast majority of the 5.6 billion air conditioners the IEA expects by 2050 will not be sitting in office towers. They'll be sitting in individual homes and apartments, where a homeowner isn't going to rip a window unit out to join an underground pipe network that doesn't exist on their street. And finally, the math only holds if the electricity charging those ice batteries at night is actually clean. China's grid still leans heavily on coal in the regions where these heat waves are hitting hardest. Shift the cooling load tonight, and you've solved the peak demand problem. You haven't necessarily solved the emissions one. This is not a lab claim anymore. This is real, and it's already running. Shanghai's number 5 cooling station came online as the largest single cooling station in all of Asia, delivering round-the-clock cooling to roughly 2.75 million square meters of buildings across the Guiwan, Tianwan, and Mawan areas of the district. Multiple stations are now operating in tandem, and Shanghai Energy expects the completed 10-station network to deliver on that full 130 million kilowatt-hour annual saving once it's finished. And the model didn't stay in Shenzhen. In Guangzhou, planners are now building an integrated energy project for the city's financial city development, expected to eventually cover around 8 square kilometers and deliver more than 200,000 refrigeration tons of cooling capacity through 8 centralized energy stations tied together by a smart distribution network. In Beijing, several landmark public buildings in the city's municipal administrative center have adopted a related approach, using ground source heat pumps that draw on the stable temperature underground instead of fighting the outdoor air directly. Here's what makes the timing impossible to ignore. Days before some of this reporting broke, in the summer of 2026, China's state grid was posting record-breaking electricity loads across its northern networks. Provinces like Hebei, Tianjin, Liaoning, and Shandong all setting new peaks within the same week, with eastern Anhui alone recording a fresh record of 69.99 million kilowatts. That is the exact failure mode district cooling with ice storage was engineered to prevent, playing out in real time in the cities that don't have it yet. Let's zoom out for a second, because this problem is not staying inside China's borders. The IEA's own modeling shows cooling could account for close to half of peak electricity load in countries like India by 2050, with similarly brutal shares projected across the United States, the Middle East, Indonesia, and Brazil. Heat waves that used to be rare are now routinely pushing temperatures past 37 degrees Celsius in cities like Paris, New York, and Seoul, cities that were never built with serious cooling infrastructure in mind. Every one of those grids is on a collision course with the exact wall China's northern network hit in August 2026. Here's the detail almost nobody talks about. China's air conditioner brands already dominate manufacturing, but that dominance has not translated into global market control. Gree, Midea, and Haier hold well over 70% of the domestic Chinese market between them, yet their combined global market share sits at only around 22%, with most of their overseas volume flowing out as unbranded manufacturing for other companies rather than as Gree or Midea, branded products people actually choose. Hardware alone, it turns out, was never going to be the real export. District cooling infrastructure might be. It isn't a box you buy off a shelf. It's a blueprint for how you design a city so it never needs that many boxes running at once in the first place. So here are a few predictions worth sitting with. 1. Expect new special economic zones across Southeast Asia and parts of the Middle East to copy Shanghai's approach at the master planning stage, not as a retrofit years later. 2. Expect Chinese engineering firms to start exporting district cooling design and operating expertise the same way Chinese brands already export appliances. 3. Expect older Chinese megacities to pilot this only in new central business districts, while most existing neighborhoods and most homes keep running on individual units for at least another decade. 4. Expect every fresh summer heat record to push more grid operators toward ice storage as one of the only tools that can shave a demand peak without building an entire new power plant to cover a few brutal afternoons a year. So here's a question worth asking yourself. Does the future of staying cool look like more boxes crammed into more windows, city after city, grid after grid, straining the same way China's did in August 2026? Or does it look like what's already running underground in Shenzhen? A city engineered from the ground up to never need that many boxes at all? Let me know what you think in the comments. And if you want the next deep dive the moment it drops, subscribe before you go.